Hello, my name is Wang Yuntao. I'm here to present our work on ICML25, finding Wasserstein Ball Center, efficient algorithm and applications in fairness. First, I'm going to talk about the background and motivation of this work. We all know that Wasserstein distance measures the disparity between probability measures mu and nu. In equation 1, you can see that the Wasserstein distance between mu and nu minimizes the transportation cost among mu and nu over all couplings between them. Wasserstein distance has a wide range of applications in machine learning community. When a space is endowed with Wasserstein distance, a space of probability measures, we can compute the Gaussian mean over it and call it Wasserstein Barycenter. In this case, given probability measures mu1 to mu_k, the Wasserstein Barycenter mu bar minimizes the weighted sum of Wasserstein distance. The Wasserstein Barycenter has also been widely applied in image processing, computer graphics, all kinds of fields. However, the Wasserstein Barycenter may behave unfairly to minority inputs. That's to say, the distribution we support deviating from the majority of others could be too far away from the Wasserstein Barycenter. Here's an example. The input distributions is the red, yellow, blue, and green point cloud. You can see that the red point cloud is separated. It's much more deviated from all other three point clouds, while the other three point clouds seems to be clustered in one cluster. So the purple point cloud is the Wasserstein Barycenter of all three point clouds. Sorry, of all the 4 point clouds. You can see that in the histogram here, the Wasserstein distance from the Wasserstein Barycenter to the red point cloud is much bigger than that of other three point clouds. So to address this unfair issue, we propose a different objective function. Rather than minimizing the summation of Wasserstein distances, we try to find a distribution that's of minimal distance from the farthest input distribution. In equation 3, you can see that the Wasserstein Ball Center minimizes the maximum Wasserstein distance from mu to all input distributions. In this example, the brown point cloud is the Wasserstein Ball Center for the 4 point cloud for input point cloud. You can see in this histogram here the maximum Wasserstein distances is much smaller than that of Wasserstein Barycenter. So how do we optimize this problem? So we only consider the case when the support of the Wasserstein Ball Center is fixed. In this case, the problem can be transferred into a linear programming problem by applying a select variable gamma. Gamma indicates the maximal Wasserstein distance from the Wasserstein Ball Center to the input distributions. So basically, we minimize gamma with the variables, W being the weight on the fixed support. Since the support is fixed, we only have to optimize the weight on it. And capital pi to t here is the coupling matrix between the Wasserstein Ball Center to the teeth input distribution. The S here is a convenient way to make sure that all those variables to be the probability measures. The backbone of our algorithm is the predictor corrector intermediate point method. This method optimizes the problem along a central path, which is a smooth path moving toward the optimum, by alternately update on the predictor step and the corrector step. The predictor step moves toward the optimum, yet it may approach the boundary, and the corrector step returns to the central path. The reason why Malhotra proposed the predictor corrector version of IPM in the 1990s is that both the predictor and corrector step can be solved directly from this normal equation or the form of equation 5. Since they can be solved explicitly, we don't have to solve the central path by some complex convex optimization algorithms. So in our case, in the WBC problem, the coefficient matrix of the normal equation is of this one. Here, B1 is of size M, which is the sum of all input support sides. B3 and B4 are both of size Nm. So you can see that the scale of the WBC problem is quite large. For example, when we consider the image dataset, such as ImageNet, in this case, the support size for one distribution would be tens of thousands. In this case, this matrix is too large to directly compute its inverse, so we must simplify it. We try to transform the coefficient matrix to be block diagonal so that we can solve its inverse by computing the inverse of several much smaller matrices. Noticing that B1 is diagonal, we first design this transformation matrix Q, which is easy to compute since B1 is diagonal, and L is a scalar, and turn the coefficient matrix to this nearly block diagonal form. However, the K2 here remains hard to eliminate. So how do we eliminate K2? We have the following observation with some careful computation. First, G1 is block diagonal, and G2 is just some replication of a smaller matrix over a much smaller matrix Y. And the size of submatrices of G1 and G2 is the same. So this indicates us to treat G1 and G2 as matrices with each term being a small matrix, just of the same size as Y. And since G2 has this quite special structure, we can utilize the Woodbridge inequality blockwisely and obtain a solution for G1 for this linear equation in nm squared times. Without this observation, this linear equation would have to be solved in n to the 2, n to the power of 2, m to 6, which requires much more time. So since now we can inverse G1 plus G2 really fast, we can diagonalize the rest of the coefficient matrix, which means we can eliminate K2 easily and solve the normal equation efficiently, in which case we would have to solve the inverse of these three matrices, and D1 being diagonal, and D1 plus and G1 plus G2 is easy to inverse with this corollary. And the W bar here is of size n, which is usually small in real-world applications. To sum up, we simplify the solution of equation 5 by the following process. First, we transform the coefficient matrix to be nearly block diagonal. Second, we efficiently compute the inverse of the core submatrix that seems the most complicated. Third, we apply the second step to transform the coefficient matrix to be block diagonal, multiplying its inverse to F, then transform it back to delta Y. The time complexity of this algorithm is n times smaller than vanilla IPM, and due to these observations of those peculiar matrix structure and the sparsity, we also our algorithm also requires this memory usage factor in that. Now we talk about some empirical research we have done. First, we compare our algorithm with the state-of-the-art commercial solver Groovy. We can see that our algorithm is consistently faster than Groovy in small problems, and when the problem scale increases, as the problem scale increases, Groovy can no longer perform normally, and our algorithm remains stable. Then we compute the Wasserstein Ball Center and Wasserstein Barycenter on real-world datasets. Surface is dataset of phase attribute for balanced race, gender, and age. The WBC performs better than WB in capturing diverse racial representation. We also compare the variance of Wasserstein distances from the obtained center to the input distributions. We denote this feature as VARWD, where smaller VARWD indicates reduced disparity between inputs. Surprisingly, across all 2,700 experiments, the WBC consistently achieves lower variance compared with WB. We haven't proved this yet, but this just means that the WBC have a better global fairness property. In addition to just place more importance to the minority input, the WBC also treats every input distribution more equally. Last, we implement the WBC to 3D point cloud averaging tasks. In this task, the input distribution is the point clouds. In this case, 3 cars and 1 chair. You can see that the WBC, which is the first figure, well, let's first see the WB. The WB, which is the middle figure, looks just like a car, while our WBC preserves the more characteristics of a chair, such as the legs, the backrest. This indicates WBC's potential to diversify the features of the ensemble result. Thank you for your attention. You can leave your comments in the comment section. We will reply to it immediately. Thank you.